Hi, everybody. This is Mr. Folly, and welcome to podcast 2.2. We're going to talk about isotopic notation, average atomic mass, parts of the periodic tables, and properties of protons, neutrons, and electrons. So let's hop right to it. What does this mean? Well, this 34 number here is the mass number. Okay, and mass is the sum of protons, which I abbreviate P positive, plus neutrons, because protons and neutrons have roughly the same mass. Okay, electrons are not included because electrons weigh something like 10,000 times less. Wow. Okay, this is the number of protons. Okay, the number of protons is also called Z, and it's also called the atomic number. Okay, and that identifies the atom. So if you have a periodic table and you're looking at S, then you can figure out that it has 16. That's the whole number on it. Proton determines the identity. Neutron determines mass and nuclear stability. Electrons determine charge and chemical reactivity. I guess it'd be chemical stability too. So there's a difference. Both of them have the reactivity. This would be a nuclear reaction, and this is a chemical reaction. Okay, so it's important to see the difference there. Where does the mass from the periodic table come from? Scientists chose. They just had to pick something. They chose carbon-12, which is in all living things, the most abundant form of carbon, and they knew its mass was roughly 12. So they defined carbon-12 as being 12.000 boop forever. This gave us the mass of a neutron and protons. Now, neutrons and protons are very close to having the same mass, but they're not identical. Okay, we average every atom of each isotope to get the average atomic mass. Okay, so that means we talked about how there's carbon-12. That's how we identify them, is by the mass. There's carbon-12. There's a carbon-14. So you would think, oh, well, then the average is 13. This is not a 50-50 ratio. Okay, it is something like a 99.9 to 0.1 ratio. It's even smaller than that. To make life easy, we say a proton and a neutron weigh 1 atomic mass unit. So we made up a unit of 1 atomic mass unit, and we truncated some decimal points to say that that's it. Okay, and we say an electron equals 0, roughly, atomic mass units. It doesn't really weigh nothing. It just weighs almost nothing. Okay. There are 3 isotopes of hydrogen. One is, we just call hydrogen. Hydrogen 2 is deuterium. By the way, the number down here would always be the same, the number of protons. Deuterium, 2. And 3 is tritium. What is the average mass of hydrogen? Well, you'd probably, your gut feel, except for you've taken chemistry before, is the average of these 3 is probably 2. Okay? It's not 2. The reason why it's not 2 is because it's 99.999-ish% hydrogen 1. Whoops, I put my 1 on the wrong side. Hydrogen 1. And then hardly any. And hardly any. About 0-ish. About 0-ish. Enough to keep the average mass from being perfectly 1. So if you look at the periodic table, the average atomic mass of hydrogen is 1.01. Why? Because there's lots of 1. And then you have an itty-bitty amount of deuterium and tritium. Concept questions. So, how many carbon atoms weigh 12.01? Notice that's the mass from the periodic table. 0. Okay? If I told you the average grade in AP chemistry was 87.6512, how many people do you think have 87.6512? Okay, that's not what I said, but you get the idea. Percent. How many people do you think have that? Probably none. Right? Probably none. So that's kind of the deal. But that's the average. How likely is it that if I grab one boron atom, it will weigh 10.8? The likelihood is 0. Why? Because boron there's a boron 11, and there is a boron 10. And that's it. There's not a 10.8. Remember how in class we were talking about how atoms are whole substances, and you can't take parts of them. This is one of those things. Average atomic mass, naturally occurring europium, consists of 2 isotopes with masses of 151 and 153. Europium-151 has an abundance of 48.03%. Europium-153 has an abundance of 51.97%. What's the atomic mass of europium? So what I'm going to do here is, we know averages, we know it should be a whisker closer to 153 because it has a greater abundance. So what does it look like when I do this? So what I do is I'm going to take my percentage in decimal form, 0.5197, and multiply it times the atomic mass. And that is going to give you 0.5197 times 153 is 79.51. And then I'm going to take 0.4803 times 151. 0.4803 times 151 is 72.5253. I suppose I'll throw those ones on there too. So the average mass is going to be the sum of these. So it should be pretty close to these two. And it should be a whisker closer to 153. So let's add them up. And I get 152.039. And if I do that, my average atomic mass, I guess I could make that 04. That's my average atomic mass of europium. It's a whisker closer to 153 than 151 because it has a greater abundance. So now I don't, AMU would be the units, or grams per mole. I don't divide by anything. It would be as if I said I have 48.03 and 51.97, and then I would divide it by 100, like 100%. But I just use the decimal form, and I think that's shorter. E equals mc squared. We lose, that's squared. Sorry, I should have fixed that by now. We lose some mass to binding energy. So when protons and neutrons are stuck together, a little bit of their mass is converted into energy, which holds them together. Because realize, if I have a proton next to a proton, those charges will repel each other. Like charges repel. So let's say that Charlie repels you. Well, if Charlie repels you, then you're probably like Charlie, if this is chemistry class. Oh, look, everybody's like Charlie. Maybe not. Calculate the average atomic mass of magnesium using the following data for the. So what this means is, so if I have 36 protons plus 47 neutrons, the mass does not equal the sum of those. The mass is a little less. And if I give you the mass difference, the change in mass, you can figure out the binding energy. Or if I give you the binding energy, you could find the change in mass. C is the speed of light, by the way. This is the mass. This is energy. And C is the speed of light, which is something in the neighborhood of, I can't remember for sure. It's something like 3.00E8 meters per second. I don't know if that's right. Check that. That's probably an extra credit question for you, because I don't remember the speed of light. That's sad. Calculate the average atomic mass of magnesium using the following data for magnesium isotopes. So again, remember what I did was I took the mass times the abundance. Now notice they put it in decimal form for me already. Alright, so I just multiplied those things and got a number. And then I'm going to add all these up. So how do I find the average atomic mass? Mass of the isotope times the abundance in decimal form, and then add it. 23.985 times 0.7870 is 18.8762. 24.986. It's much more likely to have decimal numbers. 0.1013. 2.5311. And of course this number is smaller because the abundance is so much less. 25.983 times 0.1117 is 023. And then I'll add those together. Whoops. So 2.9023 plus 2.53108 plus 18.876 is 24.31 AMU. Alright, periodic table. Oh, what was I going to say for the periodic table? There was some Lilo thing that I had for this. I forgot. I should watch my own podcast. So a row, I know what it is, families. A row is a period. So on your periodic table, Looks a little something like this. Whee! A row goes across. A column is a group which goes up and down. So this would be the first column, this would be the second column, this would be the third column. We kind of ignore this middle part and the bottom part for the most part. And a column is also, or group is also called a family, like ohana. And in chemistry, a family, or ohana, means that you have similar properties. In Lilo and Stitch, ohana means no one gets left behind or forgotten. You do need to know the names of these. So basically this is read them and learn them. There's not a huge trick to these guys too much. But again, periodic table, bam, 1, 2, 3, 4, 5, 6. This is group 1A. This is 2A. This is 3A, 4A, dot, 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 all the way up to 8A. Okay, so you've got your alkali metals, your alkaline earth metals for the first two. This is called the boron group, carbon group, nitrogen group, oxygen group, and then this is where it goes back to that funny one again, the halogens. Okay, and then 8A is the noble gases. Important regions of the periodic table: nonmetals, metalloids, metals. Where's my picture of the periodic table? Oh man, I drew one. I thought it was on here. It's coming up probably the next slide. Okay, on your periodic table, 1, 2, 3, 4, 5, 6. There's a little stair steppy that goes through there. The nonmetals are on the right of that stair step. So these are the nonmetals. Non-metals. And the metals are on the left of the stair step. Here are the metals. And the metalloids have two sides on the stair step. Two sides on steps. Now the exception to that is aluminum, and you should know that aluminum is a metal. If not, again, I think Psych still has spots. Transition series. That's this little crossbar right here. This is the transition series. We don't do tons with it, but you should need to know where it is. Sometimes called the transition metals. And the inner transition metals are the ones down here. These are the inner transition metals. And of course, there you go. I think next I do the charge of the periodic table. Well, so here is, you can see it again, stair step with a real periodic table. And it tells you all of these things that are in here. So your metalloids are these guys. And your nonmetals are over here. Your metals are over here. The exception is hydrogen, which is a nonmetal. Okay. Transition metals. Transition. And inner transition metals. Wiggly, 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 wiggly. Properties of metals. You should do this just by thinking about aluminum. Think about aluminum cans. They are shiny. Not shinny, shiny. They conduct heat and electricity. They are malleable, which means if you hit them with a hammer, they bend. That's bendable. They are ductile, which means you can turn them into wires. Okay? And those are pretty much the properties that they're usually solid. The one exception at room temperature is mercury. And they have variable bond strength. And what that means is some of them are soft, some of them are hard, some have high melting points, some have low melting points. Properties of nonmetals. Nonmetal. That cracks me up. It's basically the opposite. So if you put down the opposite of the last ones, oppose it. Well, I did it again. Opposite of the other ones. So nonmetals are not shiny, but they are dull, right? They are poor conductors. The opposite of the word malleable is brittle. They are not ductile, and they are usually gases. Properties of metalloids, they are a combo of properties. Not bad at both, combo of properties. So if something was a shiny non-conductor, that would indicate this is a metal property, this is a nonmetal property. Review. Know your parts of the PT. PT is periodic table, not playing time. Know what protons, neutrons, and electrons contribute. Know the difference between isotopes compared to other atoms. Oh, you know what? I didn't say that. What's the difference between isotopes? Isotopes have a different number of neutrons. And different atoms have a different number of protons. And you should remember that it's cooler tomorrow. Toodles.